I'll get started.
Yeah.
All right. Hello, everyone. Thank you all for coming. So today I'm going to be talking about REUs and like how to find research over the summer, and I'm also going to be talking about what I did over the summer, which was a good blend of mathematics and computer science. But before I get started, I'd like to introduce a new officer for the club, Ryan. So,
Yeah.
Oh, hello. Please work.
All right. Yeah. Hi everyone. I'm Ryan. I've been involved with Sigma a little bit, starting last year and running a meeting and joining the officer board this year. I'm a junior in CS. Do a lot of CS theory stuff, and also web development, which is kind of sad. But other than that, I do systems occasionally, and I might be working on some of the case stuff this semester. But yeah, nice meeting everyone. I have other things to go to today, but hopefully it should be a lot of future.
Cool. Right. But yeah, so Ryan will be presenting later on the semester, something coding theory related. But for now, what is an REU? Let's just get that out of the way. So an REU stands for Research Experience for Undergraduates. Right? So these are fully funded by the National Science Foundation, the NSF, and their goal is to get people to do research in math, CS, engineering, other sciences, et cetera, over the summer at other universities. So these are a great experience. You get to go to a different university over the summer and see how they do things over there. You get to meet new people, make friends. And I don't know about you. I'm stuck in Champaign for 8 months of the year. I don't want to be stuck in it over the summer as well. So it's good to see what it's like in other places. And who knows? You might even get a paper out of it. You'll definitely give some presentations, give a couple talks, maybe get a rec letter out of it. You'll see. But there are a lot of benefits to doing RU other than just getting a research paper out of it. So obviously you can't click on links, but just the slides are uploaded. But there are a lot of online resources for finding them. So I'm not gonna click on the links, but the main ones are obviously the NSF funds them, and so they would like people to go to the programs that they fund. So the NSF maintains lists for REUs, which I've linked there. There's a math-specific site just called Math Programs, and they host applications to a bunch of stuff, not just REUs, but just other sorts of like summer camps and other opportunities that you can apply to. And there's a nice maintained spreadsheet for math and computer science REUs that I've also linked here. But yeah. So the application procedure is actually quite simple. So the first thing you'll need is what's called a personal statement. So this is going to be a statement that's going to be tailored as to why you want to do mathematics research, what you're hoping to get out of it, and why you specifically want to go to that place. So if you're applying to Texas State University, which is where I did my REU, you should be talking about like what projects are at Texas State University and what professors are there and what you're interested in. They want to see that you are actually applying to something that you're interested in. So it's quite important that you tailor your personal statement, and you should be talking about like any prior mathematical or CS or whatever interests you have, any projects. If you have past research experience, that's good to talk about, but these are also a great way to get your first foray into research. So don't think that these are only for people who have done research before. The entire purpose of the NSF funding REUs is to give people their first chance at undergraduate research. So you're not at a disadvantage if you've never done research before. You're also going to need 2 letters of recommendation. So these can be from professors, maybe you have some sort of other mentorship or independent study going on. But the point is, you'll need 2 letters of recommendation. You'll need some sort of like resume or CV. I basically use the same resume I use when applying to internships. You don't need anything super special, but you do need a resume or CV. So I know a lot of people are in the internship grind right now. You can't do an internship while you're doing an REU. It's like one or the other. A lot of REUs are explicitly prevent you from taking on internships or secondary research opportunities while doing that REU. Your whole point is to focus on the research that you're going to be assigned that summer. So the deadline for most REUs is like early to mid-March. I think March 15th is when most of my REU applications were due last time around, but some were due a little bit earlier, maybe one or two or a couple days later. But this means that if you want to get together like a well-polished personal statement and start looking at letters of rec, you should be trying to get this stuff started during winter break. So you're done with finals and you can focus on this. I don't think there's really any benefit starting earlier than that, but I surely would take advantage of winter break to get a lot of stuff started, because we all know once the semester starts, you're busy with God knows how much homework and exams. So take advantage of winter break for that. So these are mostly government funded. So that means like the primary target is US citizens, but it is possible for US citizens to get some partial funding. So for example, when I was at Texas State, they paid for housing, meals, and they gave me a stipend on top of that, which is very cool. But there were a couple people who weren't US citizens, and they worked out a deal where they would only get free housing and they would get food, but they wouldn't get the actual stipend on top of that. Or some people might get a partial stipend. So if you're not a US citizen, it is possible to get these, but that would kind of put you in a disadvantage. Get your letter writers to read your personal statement and go over your resume. They're more than happy to do that. Your letter writers have probably applied for grants and other research in the past, so they know how to write personal statements. They've probably written dozens of them. They probably read other people's personal statements and they know what's needed. And outside of REUs, there's actually a lot of other options which are open to not just US citizens. So I've linked a couple here, but so MSR is Microsoft Research, so you can actually do research at Microsoft. Google Research is also a thing, but I believe their applications are closed. I'm not sure. TTIC is the Toyota Technical Institute in Chicago, so they're a computer science research institute that's based out just outside of the University of Chicago, so they're affiliated with them, but they're their own institute with their own staff and faculty and professors. EPFL and ETH Zurich and Max Planck are institutes in Europe, which are run by universities, like EPFL and ETH Zurich are universities of their own. The Max Planck Institutes are run out of the University of Saarbrücken. So if you get into these internships, then you'll have the opportunity to travel to Europe and do research there, which doesn't sound like a bad summer to me. SCAMP is something I just found out about. They're a government defense research firm that's based in Princeton. So if you apply to this, you have to be a US citizen. You need a security clearance and everything, but this seems like a cool opportunity. And then also, even if you don't get any of these, you can do independent study. Maybe not outside the university, but you can do independent study with someone at the university. It's a good way to spend your summer still doing research or learning some other things other than doing an internship, if that's not your style. And then the other tip I would say is that I don't think most people apply to enough REUs. Once you have like your first personal statement done, it's not that hard to tweak it towards other REUs, and then there's not much work in applying. Like there's no like OAs or like interviews or whatever. You just kind of apply and you get in or you don't get in. So the time commitment to apply isn't that bad. So you should apply to more REUs than you think you should. I know a lot of people got rejected from REUs and they only applied to like 6 or 7. I applied close to 30 and I got into multiple, but I would say applied to a bunch. And I'd say only apply to ones that you're interested in, but a lot of REUs cover a wide variety of topics. So it's not hard to find a lot of REUs that have stuff that you're interested in. So at Texas State University, not only was there a pure math REU, which covered algebra, combinatorics, and statistics, so a wide variety of math. There was a machine learning REU, there was a computer science REU, there was mechanical engineering, chemical engineering, biology, a lot of stuff. So no matter what your interests are, and I'm sure you probably have multiple. I know a lot of people are interested in just more than one thing. You should be able to find a lot of programs. But outside of that, I'll take any and all questions about applying to REUs and any advice stuff. Yeah.
You mentioned applying to 30 REUs, but for the friends recommendations, like are they specific for each program or?
No, a lot of professors will write like a generic application, and then so some sites do like a centralized thing. So math programs will host a bunch of applications, and then your professor only has to upload the letter once. And then there's another one, I forget, like the NSF has their own site, which is another centralized application. So it's not too much work. And then obviously, like part of the reason you should get started ahead is so you can give the professors time to like actually upload stuff. But yeah. Anyone else have any like questions about applying to REUs, how to get into one, all that stuff? These slides have a bunch of good links on them, so I recommend you download the slides; they're already uploaded, and take a look at some of this stuff and some of the previous links. Yeah. Okay, so there's a couple questions, so I'll answer them. So so at the RU I was at, there were people who were just finished with their freshman year, and then there were also people who had just graduated and they were doing this REU in between their undergrad and graduate school. So it doesn't really matter it doesn't really matter like what year you're in. Some REUs will have like oh, you should have taken X, Y, and Z class, but like the requirements are usually pretty simple. It's usually like, oh, you should have taken at least calculus, you've taken linear algebra, or like for a pure math one, they may have asked like, okay, maybe you've taken either an algebra or analysis course, or something like that. So like the requirements are pretty low, and they aren't really looking for any specific years. So I would say if you're interested in doing an RU, just apply. And your second question was like about going to the university. I would there are like one or two online REUs that I saw, but for the most part, like, the expectation is that you will go to the place that is like giving you the funding, and you'll work in person with the people. Like usually your project will be in a group, so it's easier to facilitate like group communication in person, and then also it'll give you the opportunity to meet professors and meet other people outside of the REU at the university. But they'll pay for this travel. So like so Texas State paid for my flights, and then they paid for me for a place to stay. It wasn't the best place. It was a dorm, but it was free. But yeah, they paid for it, and my flight was also covered. So if that's a concern, there are ways to deal with that. Yeah.
So as a freshman, what are the ways to approach getting like a letter of rec?
Okay. So I would say go to professors' office hours, of course, you enjoy, and actually try to make some sort of connection with them. If like a professor can't even remember your name, they're not going to be able to write a letter of rec. And then there's a lot of advice about this online, like how you ask for a letter of rec. You don't just ask like, can you write a letter of rec? And you ask in a more nicely worded way, can you write a good letter of rec? And the professors are usually kind of upfront about like, hey, I don't think I would be able to write you a strong letter of recommendation. But and I also obviously get that as a freshman, you have taken less courses than people, so it's hard to build a relation with professors. So that can be a bit of an issue. But I would say like a very underrated strategy is like actually going to office, even if you like if it's in a course you enjoy, then you probably have questions that like go beyond the material, and then like so professors notice that stuff and they'll actually take an interest in that. And obviously like if you ask good questions if you're doing well in the class, that kind of stuff. So I would say start there, but then other than that, I mean, I think I got one of my letter writers was someone I CA courses under, so I never took a course with them, but I'd been a CA under him for a couple semesters, so that's always another opportunity. If you've done an internship, I'm sure like whoever your manager was, that's also a valid source. I'm trying to think what else. Yeah, I think that's off the top of my head. But yeah, I will admit, like, just because you haven't been in college as long, if you're a freshman, it's harder to find sources of letter of rec. That's just kind of the reality of it only being your first or second semester. All right. Anyone have any other questions? See anything on Zoom? All right, cool. Yeah. All right. So what did I do over the summer? So before I talk about the research I did, I'm going to introduce you all to one of my favorite areas of mathematics called group theory. All right. Here's a bunch of mumbo jumbo. No, I'm kidding. All right. So what is a group? So they're one of the most ubiquitous structures in all of mathematics, and they are essentially a generalized structure of something that has addition and or multiplication. So like, what do I mean? So we're going to say a group is some set G with some operation, which we're just going to denote with a dot, which is going to behave kind of like multiplication. So it's associative, just like how adding numbers or multiplying numbers is associative. It doesn't matter how you multiply, in what order you multiply it, you're going to get the same result. There's going to be some sort of identity E, such that if you multiply by the identity, you get the number back. So the classic example is if you take the integers with addition, I can add two integers, I'll get an integer, and it doesn't matter if I like take 1 plus 2 plus 3, it doesn't matter if I do 1 plus 2, then add 3, or 2 plus 3 and then add 1, I get 6 regardless. And what's the additive identity for the integers? It's 0, because anything plus 0 is itself. And then every element has an inverse. So in the integers, for every number, so like every whole number, I can find another whole number. It's negative, such that if I add it together, I get back the identity. And so this appears all over in mathematics. So like I said, the integers form this. If you take rational numbers with addition or multiplication, you get groups or real numbers. If you've taken linear algebra, invertible matrices form a group, and there's a bunch of other examples. So group theory is kind of like the study of these structures. Throughout this, I'm just going to drop the dot, and I'm going to write x, y as the multiplication of x times y in the group. I'm just going to ignore the dot for now because it gets quite annoying to write. So here's a very important example, and this is kind of what a lot of the focus is in my REU, was studying what is called the symmetric group. So these are bijections, which are a function. So a bijection is a function which has an inverse. So off the top of my head, another example of a bijection that you all might be familiar with is a function on the real numbers, which is just x cubed. Because what's the inverse of x cubed? Taking the cube root. So that's another example of a bijection. So here, this is just a bijection on the first n natural numbers. It's like if n was 3, then this is the set 1, 2, 3. And here the multiplication is going to be composition of functions. So composing bijections with each other yields a bijection, because the inverse is just going to be the composition of their inverses. And then what is the identity? Well, the identity is I'm just going to map a number to itself. This is a bijection. It has an inverse, right? The inverse is itself. And then for inverses, by definition, since to be a bijection, you have to have an inverse, and an inverse itself is a bijection, right? So if sigma is a bijection, then it has an inverse sigma minus 1, and the sigma minus 1 has an inverse, which is sigma itself, right? This is just how inverses work. So you can think of these as permuting the elements 1 through n. Another example, which will be a little bit, which also came up a lot in my research, were integer matrices. So GLNP is going to be the set of all invertible matrices. So every matrix has an inverse, and the entries are going to be integers mod p. So these are integers where, as I add and subtract them, I just keep taking the remainders modulo some prime. So the integers mod 5, if I take 4 plus 4 mod 5, that's 8, but 8 after I take remainder 5, I get 3. So 4 plus 4 is equal to 3 mod 5. So in the case where p is equal to 5. So since they're invertible, this actually forms a group. So invertible just means that there's this number, the determinant, which I can identify with every matrix. And if you've taken linear algebra, you know that the determinant is multiplicative, right? And if determinant of A is non-zero and the determinant of B is non-zero, then the product is going to be non-zero. I can't multiply two non-zero numbers and get 0. The identity is going to be the identity matrix. So if you've taken linear algebra, you'll be familiar with that. Inverses, like I said, every matrix is invertible, so we have inverses. And if you multiply them, you'll get the identity back. If you've taken linear algebra, these are just the invertible linear transformations. So a very core problem in group theory is if I take two groups, how do I tell whether they're the same or not? And what do I mean by the same? So here at the top, I have 3 permutations. Okay, and the way you're going to read this is like the top is the input and the bottom is the output. So for the identity, 1 goes to 1, 2 goes to 2, 3 goes to 3. Sigma is going to be the permutation, which takes 1 to 2, 2 to 3, and 3 to 1. And then sigma squared is, I'm just going to do sigma twice. I'm going to compose it with itself. So 1 goes to 2 and 2 goes to 3. So sigma squared, 1 goes directly to 3, etc., etc. So does this kind of make sense? Right? So these are invertible. And then here I just have the integers mod 3. So 0, 1, 2. So here I have some permutations. And here I have integers mod 3. So we're with the operation addition. So we're going to add and keep the remainder mod 3. So 2 plus 2 is equal to 1 mod 3. So I'm going to say that these groups are the same in some sense. And can anyone kind of see why they might be the same? Yeah. Yeah. So I'll repeat it louder for so that the people on Zoom can also hear. If you combine the elements in corresponding columns, you get the third element. So kind of as an example, so I can map the identity to 0, sigma to 1, and sigma squared to 2. And these preserve the operations, right? So just as a very quick example, if I compose sigma with sigma squared, by what I said, that should be the same as doing 1 So here my operation is composition. I'm going to map it, and my operation becomes addition. And so what's 1 plus 2 mod 3? 0, right? So then I'm claiming that if I compose this with this, so sigma with sigma squared, I should get the identity. So I'm going to take sigma. Let's just find what the composition on 1 is. So first it's going to act on sigma. So 1 goes to 2. And on sigma squared, 2 goes to 1. We're good so far. Here, 2 goes to 3. And then 3 goes to 2. We're good. And then 3 goes to 1. And 1 goes to 3. So their composition is the identity, like I promised. And then you can also see the same thing with just composing sigma. 1 goes to 2, 2 goes to 3, 1 goes to 3. So sigma composes sigma, sigma squared, and 1 plus 1 is equivalent to 2, mod 3. So in a sense, these are the exact same group. I've just relabeled the elements. And so these are what I'm going to call, or this is what mathematicians call isomorphic groups. Okay? They're the exact same, their structure is the same, they're just labeled differently. Right? And then similarly, if you compose this with itself 3 times, you get the identity, and if you add 1 to itself 3 times, you get 0. Right? So that kind of broad idea makes sense? All right. So another big theme in group theory is we don't want to just consider how groups kind of behave with themselves, right? So all I've talked about is kind of multiplying group elements with themselves. But we also might be interested on how groups interact with other sets. So I'm going to let omega be some set. I'm going to define a group action, right? We're just going to take an element in the group and some element in the set and spit out a new element in the set. And this is going to have some properties. So the identity did nothing in the group. And so I'm going to want the identity to do nothing for my action. So if I let an identity element act on some element in omega, I just want to get that element back. So identities still behave like identities. And then again, I also kind of get this associativity thing where if I let H act on X and then let G act on the result of that, that's the same thing as just multiplying G and H and letting that act on X. And so we're going to denote this as just G with an arrow on omega. And to prevent confusion, I'm going to keep this dot when I'm talking about the action, and I'll omit the dot when I'm talking about the multiplication. So you can kind of see it here. I kept the dot when I was talking about the action, but I omitted the dot when talking about the group multiplication. All right, just hopefully keep the notation a little bit less confusing. All right. So here's some examples. So again, I'm going to let the symmetric group be G, and I'm going to let omega be the elements 1 through n. So the integers 1, 2, 3, all the way up through n. So let's just say I have some element I in here, and I have sigma, some bijection. What would be a good choice of action? Right? This is see how sigma I is a very suggestive notation. I have a bijection from the set bracket n, and I have an element in bracket n. What would be a good action choice? How I just apply the function, right? This satisfies everything. I can, if I take the identity, right? So if sigma is the identity, I'll get I back. And I still get that associativity that I was talking about earlier. And then very similarly, if I have G is some group of invertible linear transformations, so that GLNP that I was talking about earlier, and I have some vector space V, I can define a similar action where T is some transformation on vectors and V is some vector. I'll have the same thing. So I have this function, this transformation, and let it transform the vector. And I'll output some new vector. And this is one of the most important examples of a group action. All right. So just like how groups have structure, group actions have their own structure. So the important thing here is this thing called an orbit, where the orbit of some element alpha is I'm just going to let the group G act on alpha and see where it takes me. And kind of like the range of G acting on that single element is what I'm going to call the orbit. It's like how far around can alpha get if you let the group act on it. And then so every element of omega must belong in some orbit, right? Because at the very least, if I let the identity act on it, then I'm going to get alpha back. So every element must be in some orbit, and a bit of a harder fact to prove is that the orbits partition the set. So you can kind of think of the orbits as like buckets of elements in the set omega. That and every element in omega belongs to exactly one of those buckets. And then the stabilizer is just going to be all elements in the group which do nothing. So the identity is going to be it's going to stabilize an element. So this will contain the identity, but it may contain other elements. It just kind of depends on how you define the action. So if you want a nice exercise, is that stabilizers are subgroups of G, which means that if I multiply two stabilizers of an element alpha, I should get an element. I should get the stabilizer element alpha back. So G and H both stabilize alpha, and their product stabilizes alpha. Pretty good exercise. So now here's the same group as before, but now I'm also gonna let 4 be a valid input. So in all of these, 4 is gonna do nothing. So this is isomorphic to the same group we had before, right? Because all the composition still holds. If I compose this with itself, I get sigma squared. If I compose this sigma with itself 3 times, I get the identity, blah, blah, blah. So you can check that it's a subgroup of S4. You can check that's the same as S3, but I'm not going to walk through that. But what's the orbit of, so here's G, and we're going to let it act on the element 1. What's the orbit going to be? So where are all the possible places that 1 can go? Yeah, so it can go to itself. So if I let the identity act on 1, I get 1 back. If I let sigma act on 1, I get 2. If I let sigma squared act on 1, I get 3. And so the orbit is 1, 2, and 3. Simple enough. What about 4? What's the orbit of 4? Just 4, right? No matter what you do, no matter how many ways you try to let this act on 4, 4 is never going anywhere. What about the stabilizer of 1? What's the stabilizer of 1? Identity. Just the identity. Right? Everyone see that? All of these don't fix 1. If I let sigma act on 1, I don't get 1 back. If I let sigma squared act on 1, I don't get 1 back. But if I let the identity act on 1, I get 1 back. So the identity fixes 1. And then what's the stabilizer of 4? All of them, right? They all fix 4. Right? So just orbits and stabilizers. Some of the most important objects in group theory. All right. So a group classification problem is just I have some property I'm interested in, and I want to identify all the groups that satisfy this property up to isomorphism. So I'm going to say isomorphic groups are the same, and so I just want to identify what are all the groups that have this property. So I know that if I have a group satisfying the property, it's in this hopefully finite list, or I can easily identify what it is. This is one of the hardest problems in all of group theory, kind of drives the whole field. And kind of just an example, even if you're checking if just two finite groups are isomorphic, right? Just by like it's a very hard algorithmic problem. Lots and lots of papers and time has been spent trying to find fast algorithms to do this. We're not actually even sure about the computational complexity of this problem, so we don't even have like good understanding of like exactly quantifying how hard of a problem it is. We just know we can't do it good. And as a more concrete example, so there are these things called finite simple groups. I'm not going to get into what simple means. It literally took tens of thousands of pages, written by over 100 authors, spanning between 1955 and 2004. And mathematicians are currently right now trying to rewrite the whole proof in a simpler format. But even in just this one specific case, it took God knows how many hours over this many years of just hard work. So very, very hard problem, but very fundamental to the field of group theory. All right. So in my research, I was interested in the property I was interested in was called rank. So we're going to let G be some group of permutations and let it act on the set of those numbers. And I'm going to fix it so where G only has one orbit. Okay, so the orbit of every single element is the whole set of elements itself. Okay, and I'm going to let G naught be the stabilizer of some element that should say bracket n. Bracket n and omega are the same thing, my bad. I'm going to let G naught be the stabilizer of one element. It doesn't matter which one, so I can just say stabilizer of one. And then so I'm going to look now at the action of G naught acting on bracket n, right? And so while G only had one orbit, G naught acting on n may have more orbits. Okay, and it's kind of like a measure of like the reach of these stabilizer subgroups. All right. So you can kind of think of it as analogous to dimension in linear algebra. So yeah, that's what I did over the summer. To get into group algorithms in programming and how I actually tackled this problem. So again, we have the stabilizer, and there's some pretty important structure. So it turns out that this number of orbits of G naught acting on n, I can actually now consider G naught as well as some group of linear transformations. And I can just count the number of orbits of G naught now acting on this vector space. So it's like the integers mod p, and I just take products of those, where everything happens coordinate-wise. Turns out the number of orbits of these are the same, but we know a lot more about the structure of groups on this side. So if I can identify the structure of the groups acting on this vector space, I can find my rank. And it turns out, in my case, G naught contained this certain special subgroup of order q to the 2n plus 1, where q is some prime. It does not matter what it is. The details are whatever. But I knew it contained this. So we now have G naught acting on this vector space and this special subgroup of this size. And so this gave me these four parameters to play around with. If I knew P, K, Q, and M, I could identify a lot of properties about my structure. And so remember what I said about how the orbits partition the whole set. So the orbits of this partition this set, f sub p to the k. And so what my group did was, now that we had these parameters, we kind of found this upper bound value b in terms of these values, where the size of my group divided b. We also know there's just like a theorem in group theory, the orbit stabilizer theorem, if anyone's curious. So the size of the orbits must divide b. So then if I consider my divisors of b, we know there's one orbit of size 1, because remember, there's a stabilizer, right? One of G naught is a stabilizer of an element, so we know the orbit of that element is just going to be one element, the element itself. And then everything else must sum up to p to the k minus 1. So f sub p to the k has orbit has size p to the k, and I know there's an orbit of size 1. So then all of the other p to the k minus 1 elements must go into other orbits. And so it turns out that my problem connected to what's called the change making problem with these coins d1 through dt and this target value. And so what is the change making problem? So in the change making problem, you have some set of denominations of coins and a target value t, and you want to make change for t using as few coins as possible, right? So if you can think of like just normal coins with like pennies, nickels, dimes, and quarters, you might want to make change for 70 cents. So then what's the most efficient way you can do that? I think it's just 2 quarters and 2 dimes. But this is a very like fundamental problem in algorithms. Like, I'm pretty sure this also appears as a lead code problem, but turns out it came up here as well. So we have some fixed set of possible sizes of orbits and this target value p to the k minus 1. And we know that the orbits partition this target value. And so I want to count the number of orbits, right? And so a worst case lower bound is the most efficient packing or the most efficient change making as possible. So if I can solve the change making problem with these divisors and this target value, I get a lower bound on my rank. So hopefully that connection is a little clear. So then how do you actually solve this problem, right? So if I have these coins, so I'm going to let num coins I comma c be the smallest possible number of coins of the first c denominations needed to make change for I. Okay. So if my set of values is 1, 3, 5, 7, the num coins 10, 1 is going to be 10, because so c is 1, so I can only use the first coin. My target value is 10. And so I only have the 1 cent coin available. So the best way I can make 10 cents using only 1 cent coins takes 10 coins. But if I allowed myself to use all 4 coins, then the most optimal way to do this is by choosing the 5 cent coin twice. So then my final answer is 2. Right? Cool. So there's a nice recursive way to talk about this. So num coins I see. So no matter what I is, if c is 0, I haven't given myself any coins to use. So how can I do anything? I can't do anything. So I'll just say it's infinity. So now let's just say I is strictly less than coin, like the Cth coin. Well, I can't make change for like, let's say 7 using a 10 cent coin, right? You can't split a coin in parts. No one would take that. So if my value is less than the largest coin, then my answer is going to be the same as just ignoring that coin and just seeing the best I can do with all the smaller coins. If I is equal to the largest coin, well, then that's the best I can do. If I have a 10 cent coin and I want to make 10 cents, I can't do better than just that one coin. And the value is 1. So now otherwise, I is larger than the Cth coin. So I kind of have 2 choices I can make. I could use the largest coin. So I'll subtract it from my total value and I'll recurse and see what can I do now with a smaller target value. And since I've used the Cth coin, I'll add 1. Otherwise, I'll ignore the largest coin. And I'll just see what I can do using only the smaller coins. And I'll take the best of both worlds. So this is kind of like a very natural greedy algorithm to do this, where I just at every step I just take the largest possible coin, but a good exercise is seeing how if you just take the largest possible coins, it's not hard to come up with an example where this greedy strategy isn't optimal at all. This actually kind of bit us in the ass when we were writing this paper. We kind of assumed the greedy strategy because we thought we fell into a certain special case, but we didn't. So we had to rewrite some parts of the paper. So at a very high level, because I don't want to get too much into the details, so we have these parameters P, K, Q, and M. We did a bunch of like actual group theory and pure math to get bounds on these parameters. It's like P is between these values, K is between these values, blah, 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 blah. So now I had a finite list of parameters. And I wanted to classify the groups of rank less than or equal to 6. So I just enumerated all possible sets of parameters. I kept the ones that have a lower bound less than or equal to 6. Because that's what I was interested in. And so now I have this set of valid parameters. And so I can find this largest possible group N, where N acts on this vector space. And then now I do some computational stuff. So I check if this special subgroup is contained, because I know it is. And this is a very hard problem in group theory. Just checking if a subgroup exists inside another group. I check if N has rank 6. This is actually really easy to do. And then we did the same process, and now this was the largest possible group. And so now I want to check if any subgroups have the same property. So I enumerated all possible subgroups of this larger group. And this is also one of the hardest problems in computational group theory. And I did this for every single subgroup that I enumerated. So how did I do this? Because I sure as hell didn't do it by hand. So we did this in a programming language called GAP. It stands for Groups, Algorithms, and Programming. But that's just one of many computational algebra systems. There's SageMath, which is built on top of Python. There's Mathematica, which some of you may have heard of. There's Magma, which is really popular in the cryptography world and was recently used to break some of the promising schemes for post-quantum encryption. And then there's Macaulay 2, which is actually created by a former professor here, Daniel Grayson, at the University of Illinois. I did all these hard computations in AWS because I am but a mere mortal with a mere mortal's laptop. And these computations got very, very intense. And as a side note, all of our techniques kind of extend to larger rank, but the computational issues and the resources needed became a very, very large issue, which is kind of why we just stopped at rank 6. In theory, if I had much more powerful computers, I could do this up to rank 12, but I don't have access to computers that size or money to pay for an AWS instance of that size. If you want more details, the paper's linked on my website. And I'm happy to explain stuff about it. I'm going to be giving a talk at the undergraduate math seminar, which is held on Fridays. I'll give the details soon because I don't know that much about it. I just know I'm doing the talk. They haven't told me that many details, but I'll post about that in the Discord. And also just feel free to either DM me or ask me stuff in the Discord if you're interested in this kind of stuff. Yeah. You have any questions? Yeah. Where did you?
No, it's not really.
Oh, okay. I just have. Anyone have any other questions? All right. Here's a nice quote about algebra, and thank you all for coming.